Okay, let's jump right in. We're talking about Kubernetes scheduling today. And look, I get it. You might be thinking it's, a pretty basic function. It puts pods on nodes. What's the big deal? But what we're going to uncover today through some real-world war stories is that in the high-stakes game of production, the scheduler is one of the most powerful and honestly complex tools you have at your disposal.
And this quote, it just nails it. This really sets the stage for everything we're about to talk about. It's not just a catchy phrase, it's a warning. It's the fundamental problem we're going to explore, all based on lessons learned when things went sideways.
So what's the real difference here? Well, in your lower environments, dev, staging, the default scheduler is a dream. It just works plain and simple. But production? That's a whole different universe. You've got multiple availability zones, service meshes, sidecars, all kinds of different workloads. And that's when you suddenly discover the scheduler's incredible power and all of its hidden traps.
And this brings us to what I call the scheduler's most dangerous assumption. You see, the lessons we're about to walk through, they didn't come from some clean, theoretical lab experiment. No way. As the source material puts it, these were 2 a.m. incidents. We're talking about pagers going off, high-stakes production failures that forced a much, much deeper understanding of how this all works.
So what is this dangerous assumption? It's pretty simple, actually. The default scheduler's #1 priority is efficiency. It wants to pack your pods onto as few nodes as it can, to be efficient with resources. But that very act of trying to be helpful can create these incredibly dangerous clusters of your application, leading to a massive single point of failure you never even knew you had.
So let's get into our first case study and see exactly how this plays out. We're calling it the availability trap. This is a story about how a system specifically designed for high availability nearly took down the whole show. All because that resilience, well, it wasn't as automatic as everyone thought.
Okay, so picture this. We've got a 3-zone cluster, and there's a critical API running on it. To make sure it's super resilient, it's running with 9 replicas. 9 copies. I mean, on paper, that sounds great, right? You'd feel pretty safe with that kind of setup. But then things go wrong. A traffic spike hits, and one of those availability zones starts having network problems. And just like that, 6 of those 9 pods, that's 2/3 of the entire service, vanish. They become completely unreachable. The whole system is now teetering right on the edge of a full-blown outage. And this, right here, this is the heart of the whole misunderstanding. A ReplicaSet makes you one simple promise. It guarantees the count. It makes sure that 9 of your pods are up and running. But what it absolutely positively does not guarantee is their distribution. It couldn't care less where they run, which is exactly how they all got piled up in the wrong place at the worst possible time. So how do we fix this? Enter a feature called pod topology spread constraints. Now, this is way more than just telling pods to stay away from each other. This is about giving the scheduler strict mathematical rules to keep a balanced distribution across what we call failure domains, like your different availability zones. And this chart just says it all, doesn't it? Before the fix, just look at this mess, a dangerously imbalanced state. You've got 6 pods crammed into Zone A, while poor Zone C only has 1. So, of course, when Zone A hit a snag, the whole service was crippled. And now, look at this. After applying those spread constraints, we get this just perfect, beautiful balance. 3 pods in each zone. Now, if any single zone goes down, you only lose 1/3 of your capacity, not 2/3. That is what true high availability looks like. It's something you have to engineer on purpose. Okay, so we've seen how to control where our pods land. Now let's tackle another super common headache, the resource ghost. And this is a story that's probably going to feel really familiar if you've ever found yourself staring at a monitoring dashboard saying, but the requests look totally fine. So here's the mystery we need to solve. Your nodes are under memory pressure. Pods are getting evicted. But you look at the numbers and the sum of all your pod requests is way, way below what the node can actually handle. The math just doesn't add up. It feels like something invisible is eating up all your resources. And the solution is another one of these hidden gems, pod overhead. It's a feature that lets you tell the scheduler about the extra resources being used by the pod's plumbing. Things like a service mesh sidecar or sandboxing runtime. It basically makes the invisible visible, which is absolutely critical for the scheduler to make smart decisions. Now, the math here is dead simple, but the impact is huge. The scheduler was only seeing the 512 megs requested by the app container. But by telling it about the 50 megabyte pod overhead, it now correctly calculates the real schedulable size as 562 megs. Finally, it's working with the right numbers.
I just love this analogy from the source material. Pod overhead basically creates an invisible container in the scheduler's math. Before using this feature, the scheduler was completely blind. It had no idea about this extra runtime overhead, which led it to pack nodes way too tightly without even realizing it.
All right, let's move on to our third and final incident, the wrong destination. This one's all about making sure we send the right kind of work to the right kind of nodes, especially when you've got some expensive, specialized hardware in the mix. So the situation was pretty straightforward and pretty painful. A GPU-heavy machine learning job gets scheduled, and it lands on a cheap spot node that doesn't even have a GPU. The result? Instant crash loop backoff. The pod just keeps starting, crashing, starting, and crashing. You're just burning money on compute cycles, and your whole ML pipeline grinds to a halt. The solution here is seriously powerful: scheduler profiles. This is a feature that lets you run multiple, totally custom scheduler configurations inside the exact same cluster. So you can get rid of that one-size-fits-all approach. You can have your default scheduler for all the normal stuff, and a completely separate specialized profile for your ML jobs that knows it needs to find a node with a GPU.
So when you pull all these incidents together, you start to see that a real shift in thinking is necessary. It's about moving from being just a Kubernetes operator to becoming a Kubernetes engineer. It's about thinking way beyond just, let me deploy this pod. And to make that shift, you have to realize the scheduler isn't some magic black box. It has a really clear three-step process. First up is filtering, where it asks, okay, which nodes could even possibly run this pod? Then comes scoring, where it ranks all those possible candidates from best to worst. And finally, there's binding, where it makes the decision and places the pod on the top-scoring node. The most important part? We can influence every single one of these phases. And this just drives the whole point home. Running Kubernetes is when you deploy pods and just kind of hope for the best. But engineering Kubernetes, that means you're intentionally designing your failure domains with spread constraints. You're accounting for all that invisible overhead. You're aligning the scheduler's logic with actual business goals. It's a totally different game. And this quote just perfectly sums it all up. The scheduler is not just a placement tool. It is a control plane decision engine. Think about that. It's not just putting pods on nodes. It's a strategic brain that you use to enforce the reliability, performance, and even the cost efficiency of your entire system. And that leaves us with one last question for you to take back and think about with your own systems. Is your cluster just surviving production day to day, or has it been truly engineered to master it? The difference, as we've seen, lies in knowing and using these incredibly powerful tools.